I think we'll go ahead and get started now since it's 11 and we want to make sure we have time for everyone's questions and our excellent talk today. Hi everyone, thanks for joining us today. I'm Kelsey Swartz. I'm the marketing manager here at Assay Quant. We're very excited to present our webinar, Validating the Power of a Continuous Assay Format Using EGFR Inhibitors in Potency, Profiling, and Time-Dependent Inhibition Applications. Please feel free to ask questions through the Q&A portal thing at anytime during the webinar, and then I will help moderate all those and we'll make sure we get them all answered at the end of the webinar. If for some reason your name's not showing, we would encourage you to use a name in case a question doesn't get answered or requires further discussion. We're happy to follow up with you after the webinar. It's my pleasure to introduce our two speakers today, Dr. Michelle Lyles and Dr. Earl May. Dr. Michelle Lyles is Assay Quant's VP of Commercial Operations. She received her PhD in biochemistry from Baylor College of Medicine and did postdoctoral training at Emory University. She joined us at Assay Quant with 20 plus years of experience in sales and marketing of advanced scientific tools at many major life science suppliers. Dr. Earl May is our Senior Director of Discovery Technologies. He comes to Assay Quant with over 25 years of experience in drug discovery and enzymology at many major pharma and biotechnology companies. He's a longtime user of our SOC sensor peptide technology, studying both reversible and covalent compounds, and they're both a wealth of knowledge about all of the topics we'll be discussing today. So I'll now pass it over to Michelle to get us started.
Thank you. So I'm just going to share my screen. This takes a couple of clicks. There we go. So thank you, Kelsey. Very much appreciated. And welcome everyone to Assay Quant's webinar entitled, as Kelsey said, Validating the Power of a Continuous Assay Format Using EGFR Inhibitors in Potency, Profiling, and Time-Dependent Inhibition Applications. So today we're going to start with a quick introduction of Assay Quant as a company, just so you know who we are in case you don't know who we are yet. We'll introduce Assay Quant to you. Then we'll do a technology overview of PhosphoSens itself as a continuous assay format. Then we'll turn it over to Dr. Earl May, and he will go over our applications for potency determination, kinome profiling, and time-dependent inhibition. In particular, we'll highlight how the continuous assay format really supercharges these applications. And then we'll end with a summary and questions and answers. So Assay Quant, who are we? Assay Quant was founded in the year 2015 based on the notion that better data provides better informed decisions. The company was founded by Dr. Eric Schaefer and Dr. Barbara Imperali. Eric has over 25 years experience commercializing and developing tools for the life science research space. Part of that is over 400 products in the life science space. And Eric has forgotten more about kinetics and kinases and phosphatases than most of us will ever learn. So he's amazing. Eric is not only our co-founder, he's also our CEO, CSO, and president. Barbara is the inventor of PhosphoSens technology, and you probably recognize Barbara Imperali's name. She's a world-renowned chemist. She is a full professor in not only one department at MIT, but two. So Barbara's a full professor at MIT in both the Department of Chemistry and Biology with over 220 peer-reviewed articles and 14 patents, also a member of the National Academy of Sciences. And Barbara's not only our co-founder, but she's also our CTO. So how do we provide better data for better decisions? We do that with innovative and powerful technology for kinases and phosphatases. And what I'd like to do is I'd like to tie the word innovative to three words: continuous assay format. So that's really important for PhosphoSens and how this technology works. We support research and drug discovery, not only with these enabling technologies, but also with world-class expertise and support, especially and in particular in the realm of enzymology. So where do we fit? Everyone is very familiar with this drug discovery continuum, starting with basic research, target ID, and target validation, going all the way through clinical trials. So PhosphoSens is available in 3 formats, and it works across the preclinical drug discovery continuum. And the 3 formats are PhosphoSens Red, PhosphoSens Kinetic, and PhosphoSens Lysate. Today, we are going to be focusing on the kinetic assay, potency, profiling, and TDI. You know what? I think what we'll do today is let's go ahead and skip this slide for today. Just let me mention that Assay Quant does have a synergized technology offering, so scientists can access PhosphoSens in a variety of formats, including full services as well as catalog assays. So I've mentioned previously that we want to tie the word innovative to 3 words, continuous assay format. So what is the innovative component that enables this continuous format? Well, it is the PhosphoSens sensor peptide. And it's shown here in this illustration, where as the name implies, here, let me go ahead and turn on my pointer here. There we go. Where the name implies, the PhosphoSens sensor peptide is a substrate for your kinase or phosphatase of choice, where the fluorophore sulfonamino-oxime is covalently attached to the peptide in close proximity of the phosphorylation or dephosphorylation site. And this sensor peptide averages between 7 and 14 amino acids in length. The SOX molecule is covalently attached, usually plus or minus 2 residues from the site of phosphorylation. It can be as far away as 5, but generally plus or minus 2 residues from the site of phosphorylation. Now, a particular note and an important note, the SOX molecule itself is very small. It's about the size of a tryptophan. So what this means is that steric hindrances contributed by the fluorophore itself is greatly minimized. It's also minimally hydrophobic. That means the SOX molecule itself is going to contribute very, very little to nonspecific binding to the fluorophore itself. The peptide sequence, how do we get the sequence? Well, we start with the physiologically relevant sequence. Then we systematically go through and substitute every amino acid with every other amino acid until we find the optimized sequence. And it's optimized for sensitivity, measured by signal to background, as well as activity measured by reaction rate. Now let's put these pieces together and see how the actual continuous fluorescence intensity format works. So here you're looking once again at the PhosphoSens sensor peptide. Here's the covalently attached SOX molecule. Here's the site of phosphorylation. So in the presence of the kinase, ATP, and magnesium, phosphorylation occurs, which then chelates magnesium mediated by the SOX molecule itself and the phosphate group, so that when you excite at 360 nanometers, you get a readout at 485 nanometers. Now, what's important here, because the molecule itself, the readout molecule itself, is covalently attached to the peptide substrate, and in close proximity of the catalytic event of phosphorylation itself, this gives you a readout that is continuous and it's fluorescent. So whenever you see PhosphoSens data where we're showing signal versus time, this is from a single assay well. So each of these little dots representing a time point is not a separate well, it's a single well. And we call that or describe that as a progress curve in every well. So here, this is an actual 384 well readout from one of our instruments in an actual experiment. And what's really neat here, because it's continuous format with a progress curve in every well, you can actually see how the experiment is laid out, right? So if I look at what is this I and J, row I and J, you can see here's my controls. If I look close, look, I can even see a dose response curve, you know, from a low concentration of inhibitor up to high concentration. So very powerful. So let's look at the information that's in the box here. I've said most of it, but let's make sure I've covered it all. So the assay format itself, it's called chelation enhanced fluorescence, and it's enabled by the sulfonaminoxene, or the SOX molecule. It's the actual event or catalytic event of phosphorylation that yields the fluorescence readout that gives you a progress curve in every well. The assay is direct, homogeneous, and accessible. So what do we mean by that? Well, it's a simple add and read format, just like you're used to. It's compatible with any plate format 96, 3D4, 1536. It's also compatible with any standard plate reader capable of fluorescence intensity. What's really important to note and what's unique is that the PhosphoSens assay is compatible with a wide range of ATP concentrations. This includes ATP-Km. This allows you to determine the potency of your compounds independent of the mode of inhibition. It also makes this ideal for ATP competitive inhibitors. It's also compatible with 1 millimolar ATP, which we know correlates with cellular conditions. So just again, calling out the fact that you get, with one well, a full-time course in all the kinetics in a single well. And the application space that we've already discussed includes potency, TDI, profiling, mode of action, mode of inhibition, etc. At the moment, we have more than 440 PhosphoSens assays available, either, as I said, as a service or in our catalogs. Now, we're not going to be showing data for our Redshift assay, but I just want to show you how it works because it's really ingenious. So what we do is you start off with the continuous assay. Okay, so you recognize this, right? Here's the PhosphoSens sensor peptide. In the presence of the kinase, ATP, and magnesium, we get the chelation event, excite at 360, readout at 485. Now, what you can do is you can stop the reaction, add europium. Europium has a higher affinity for this chelated complex as opposed to magnesium. So europium is going to replace the magnesium or displace the magnesium. So now what you will get is a redshifted assay where you excite at 360. Then you get you excite the SOX molecule at 360. There's an energy transfer to europium, and now in a time resolved fashion, 100 microsecond delay, you're going to get a readout at 620, which is redshifted. So this is ideal for if you've got autofluorescence, compounds that are autofluorescing. Well, you know, autofluorescence, number one, is usually in the blue range. So by shifting the assay to the red range, you won't see that. Also, autofluorescence generally is in the nanosecond time frame. This readout is in the microsecond time frame. So autofluorescence is over by the time you do the read. It's also ideally suited for high throughput applications where you want to stop the reaction and read later, especially when you're using plate stackers. So application areas, as I had mentioned previously, all across the drug discovery continuum, preclinical, starting with basic research, all the way through, but not including clinical trials, at least not yet. So here is a list of our application areas. And today, what we're going to be focusing on is drug potency, kind of profiling, and time-dependent inhibition. And as the title of our webinar implied, we're going to be showing you these applications validated with data employing EGFR and known EGFR inhibitors. So let me try to read these inhibitor names. I always have trouble reading these names. It's ironic since I work for a company that specializes in kinases, right? But anyway, here we go. The known inhibitors for EGFR are gefitinib. Here we go, gefitinib, which is a reversible, fast-off, time-dependent inhibitor. It is ATP competitive. Lapatinib, which is a reversible, slow-off rate, time-dependent inhibitor, also ATP competitive. We're going to be looking at osimertinib, which is an irreversible, time-dependent inhibitor, ATP competitive. Lazertinib, which is irreversible, time-dependent, and ATP competitive. And we threw in staurosporin as a well-known control. It's a pan-active inhibitor, It's not time-dependent does not show time-dependent inhibition, excuse me, and it's ATP competitive. So with that, I am very happy to toss this over to Earl to dig in deep into these applications.
Great. Thank you very much, Michelle. I'm going to kick off. I'll tell you a little bit more about these inhibitors, and then we'll launch these into drug potency, kinome profiling, and time-dependent inhibition, and how that works with our assay system. So gefitinib and lapatinib are first-generation inhibitors that came out of AstraZeneca and GSK. They're as Michelle said, they're reversible inhibitors, but they differ in their off rates. Gefitinib is your kind of typical fast off rate inhibitor, whereas lapatinib is a slow binder. Osimertinib and lazertinib, osimertinib comes out of AstraZeneca, and lazertinib comes out of a collaboration between Yuhan Pharmaceuticals and Janssen. They're both irreversible third generation inhibitors, so they represent the irreversibles. We'll get to that in a second. And storosporin is just in there as a control. It's pretty much the poster child for promiscuous kinase inhibitors. Everybody uses it as control, as do we. So let's launch right into it here. I'm going to go right into our dose response and IC50 work that we do. So when we do this internally, and as Michelle said, we can sell these peptides, so people can do this in their own lab as well. It's trivial to do, but a lot of folks like us to do it. When we do it, we do 12-point dilution series in our dose response, and we can do it at 1 millimolar ATP or at the km for the enzyme. Typically, we do it without any pre-incubation of the enzyme with the compound. That's important because it is a continuous assay format, and if you do it with the pre-incubation, you kind of lose that extra information that we're offering here. So it's almost the exact opposite of what I used to yell at medicinal chemists when I was in drug discovery. I used to say, always pre-incubate, always pre-incubate. Well, with a continuous assay format, you don't want to pre-incubate because you want to capture those progress curves from the start. And then we report IC50s derived from the initial rates of the experiment. And that's the important thing. We're actually looking at rates here. We're looking at slopes. We're not looking at an endpoint and assuming that it's linear from there to the origin, and therefore it's directly proportional to the rate. So as Michelle said, all of this data, each one of these curves is from a single well, and it's all enabled by our continuous assay format. So here are the dose response curves that you can pull out of these, again, from the initial rates from what we derived there. And we can plot all of those and report those to you with our error. And if we have enough information about the Km, the concentration of ATP used, the concentration of the enzyme, all the stuff that goes into the Chang-Prusov equation, we can report a Ki to you. And so typically we have the caveat there that we're assuming it's purely competitive in our typical report. Okay, these are continuous assay formats. So you can look at these, you can say, what do these look like? Well, you can say, for the dose response for storosporin and for gefitinib, those look pretty linear straight from the get-go. But when you look at the dose responses for lapatinib, you can see they start off with a rate and they sort of slope over to another rate. Okay, that is time-dependent inhibition. All right, the inhibition depends on the incubation time that you have there. So if you're going to get an IC50, you're going to get a different IC50 if you take it at this point as opposed to taking it at this point. And if you're doing a slow off-rate inhibitor, then the best IC50 to report is the steady state velocity over here. But really, it's best to report kinetic parameters for any kind of time-dependent inhibitor. But before we report anything, we need to know whether this inhibitor, this time-dependent inhibitor, is reversible or irreversible. Okay, so quickly, here's osimertinib and lazertinib. you can see here that not only do these curves fall off very quickly, and often they're plateauing at 0 for this rate. And it's possible that these are actually in the process of totally going to 0. You don't know that until you go out further in the reaction, or if you actually do a reversibility test here. So we don't know at the outset. I mean, we know because these are very well-known commercial inhibitors here. We don't know from the outset whether these are reversible or irreversible, but we will report IC50s. But it's important to note, and this is a common phrase, which you'll see in the literature, hopefully, that if you're working with irreversible inhibitors, IC50s are going to be misleading you. All right. You really need to have kinetic parameters for a irreversible inhibitor to best describe potency of that compound. And we'll get to that in a second. So that's dose response testing IC50s. Now we want to go right into kinome profiling here. So we've got our gorgeous Assay Quant kinome tree, which we've only just recently launched. It is both pretty to look at, but is also phylogenetically accurate with all of the known kinases that are plotted up there. And the shrubs at the bottom are atypicals that are distantly related, pseudokinases, compounds, kinases like that. So right now we have a total of about 400 distinct wild type kinases and growing. Right now we can test at any ATP concentration. We got a pretty quick turnaround here, typically a 10-day turnaround with a detailed report that comes out of this. And the report supplies 4 things to you. It gives you a table with a heat map with all of the kinases and the percent inhibition you get against each of those kinases in tabular form. We also give you a waterfall plot, which basically goes from the most strongest hit kinases all the way down to the weakest hit kinases. That quickly gives you an impression of the selectivity. And for any of the most potent kinases, we supply a bar chart for those that details the percent inhibitions for those in a bar chart form. And then, of course, you get this tree. So you can look across the entire panel and get a visual representation of this. So next, I'm going to give you some examples of some profiles using the inhibitors we just talked about. Here's staurosporin, our ATP competitive promiscuous inhibitor. If you do at a relatively low concentration for staurosporin, 100 nanomolar, you still hit an awful lot of kinases when you do your profiling with the ATP concentration equivalent to the EGFR KM for ATP. Okay, and you can see from this waterfall plot, you get an awful lot of kinases that are hit at this concentration. About a quarter to a third of all of the known kinases are hit by this, and you can see them, all the various leaves for these kinases lit up here. Okay, if, however, you do this with a higher concentration of ATP, 1 millimolar, close to approximately physiological concentrations, you can see that many of the kinases that are hit by staurosporin are washed away by ATP. It's an ATP competitive molecule. So you can see in some of these trees here that some of these leaves are no longer red. Over here, they've shed just like in autumn, and that's a good indication right there of the competitive nature of our inhibitor here without doing a full mode of inhibition analysis. Next, we've got the, let's go back to this. Next, we have gefitinib, Iressa. Here is at ATP. With ATP at KM, we're only lighting up EGFR here. It's very, very selective inhibitor here under this relatively low 15 nanomolar concentration. If you go up higher in the compound concentration, you'll start to get some off-target hits as well. However, if you add more ATP to this reaction, of course, that will wash away that hit there. Similarly with lapatinib, if you do it at 85 nanomolar lapatinib with ATP at the KM for EGFR, it too lights up just EGFR. But when you add ATP at 1 millimolar, that washes away right here. Osimertinib, our first irreversible inhibitor with this, you can see it will hit a few kinases here, including mostly the HER family and some of the closely related tyrosine kinases down here. Add up to 1 millimolar ATP, however, at this 90 nanomolar concentration, and you can see they wash away. And finally, I don't have lazertinib for this, so we'll just go right on there. So that's our profiling service. It is not only reports out the percent inhibition here, it also supplies a few other important things. We can look, because it's a continuous assay format, we can actually look at the progress curve for each one of these reactions and give you some kinetic insights from that. Those come in typically two flavors that we're most excited about. The first one is, of course, if you add 90 nanomolar osimertinib to EGFR at KM, you can actually see the activity falling off, even with that one concentration across the full panel of 400 some enzymes. You can see that time-dependent inhibition happening right there. That right there we'll see as a flag. Our automated data analysis system will pick that up and make sure that we note it in our reports, so that when you're doing a screen or profiling of something, you'll know this is something you can follow up with in our TDI workflow, which I'll get to on the next slide here. Also, we have something we've been monitoring over the last couple of years of compound-specific lag extension. That's where you add your inhibitor, and it first inhibit you see a delay in the onset of the activity, but then once you actually see the activity, it goes up to a linear progress curve. So that lag actually increases with higher and higher compound concentration. We're not 100% sure of the science behind this. The simplest explanation is that these inhibitors are inhibiting the autoactivation of the enzyme, which is normally very fast in our DMSO controls here. That's the simplest explanation, but we have another series of hypotheses. They could be something that's specifically hitting compounds that are in the inactive conformation, or they are compounds that are hitting different oligomeric states of the kinase with different IC50s. Where we haven't had the time since we first noticed this to fully interrogate this, but it is something we'll flag for you. And if there's necessary follow-up from that, then we can definitely go on from there. Okay, so that's profiling. Let's say you see something like this. You see some time-dependent inhibition, and you want to know more about it. Well, we've developed over the last year or so a workflow to fully identify, interrogate, and characterize time-dependent inhibitors. We have, it's a three-step process, and it starts with a simple dose-response test with and without pre-incubation. Okay, here we're actually doing pre-incubation because we want to see if there's a difference. And we look at that, and we look at the progress curves, just like we did before, but we'll also see if there's a shift in the IC50s with and without the pre-incubation. Okay, once we do that, if we don't see a shift in the IC50s or any kind of divergence from linearity, then that just means it's one of our standard fast-off inhibitors, and we will be able to report IC50s and KIs, as we talked about at the beginning here. If, however, it is time dependent, the next step is to find out if it's reversible or irreversible, because how we characterize this kinetically depends upon whether it's reversible or irreversible. If we don't know, we can get bad numbers out of our step 3 experiments. We typically do that through a jump dilution experiment, which I'll detail in a second, or we also have a new method that we're developing here. So that tells us whether it's reversible or irreversible. If it turns out it's reversible, then from those jump dilution or free compound clearance experiments, we can actually determine the off rate and the residence time for that reversible inhibitor. If it's actually irreversible, Then we have another series of experiments that report the kinetic parameters necessary to describe the potency for covalent inhibitors. And those are the inactivation efficiency, K-inact on Ki, and then also K-inact and Ki separately, if possible, if we can separate those two. So here is what it looks like for the first step. We do plus or minus pre-incubation. For sporin and gefitinib, we see that whether it is with or without pre-incubation, they both all the curves look fairly linear, straight from the origin, and just by visual inspection, it doesn't look like there's that much difference in the IC50s, and we'll tabulate that in a bit. However, if you look at osimertinib and lazertinib, there's dramatic changes in the shapes of these curves with and without pre-incubation. Without pre-incubation, you see them keeling over like this. With pre-incubation, you see things are fairly linear, but you can definitely see that there's a shift in the IC50 by all these higher concentrations clustered at the bottom. And these linear curves that you see here are most likely the result of not enough inhibitor to cover all the enzymes in the reaction. And so that's the activity of the leftover enzymes that haven't been deactivated. Same story for lazertinib here. So now we look at this. We say, is there a shift in the IC50s? And what we tend to look at is with a fold change between the two. And our rule of thumb is anything is greater than 2, we're going to be looking at more closely here. But really, we've got huge differences in the IC50s for our irreversibles here, all right? But here for lapatinib, for example, it's not quite a big difference there, but you can still see from the progress curve that it definitely requires some closer examination here. So that takes us to our next step in this reaction. We've identified the time-dependent inhibitors. We want to know if they're reversible or irreversible. And we typically do this through the tried and true jump dilution protocol, but stay tuned. We've got a new protocol we're very excited about that will make this a lot easier, because I'll let you in a little secret. Nobody likes these jump dilution experiments. They are troublesome. There's a lot of caveats to them, which I can describe later if anybody's interested. But it's a very simple protocol. You pre-incubate the inhibitor with the enzyme at an inhibitor concentration 10 times over its IC50. And then you rapidly dilute it 100-fold so that it is now at 1/10 of its IC50. That means you have to do the original pre-incubation at 100-fold the enzyme concentration, which introduces a whole bunch of problems with this. But then immediately after you dilute it, you start the reaction with the addition of ATP, and then you basically watch the recovery of the activity over time. If you've got a fully reversible inhibitor, then you can see that it recovers fairly quickly to a slope that's, well, 1/10 of the DMSO control here. That's the 1/10 the IC50. The slope is consistent with that. I guess it's about 1/9 or something like that. If, however, it is irreversible, then you don't see any recovery of activity. And if it's a slow binding inhibitor, then you can see that the recovery is delayed here, like that. And so now we know if it's reversible or irreversible. We take that information and go into the third step of the reaction, of the experiment. And actually, here's a detailed example just looking at a close-up of this, and you can see for gefitinib, it's a very quick recovery. For lapatinib, it's delayed here, okay? And that for lazertinib, you don't see any recovery whatsoever. All right, so now we know it's reversible or irreversible. Now we can go on to step 3, and we have a 3A and a 3B. If it's a reversible inhibitor, then you do a couple extra jump dilutions, and really to satisfy many of the caveats, which I'm not going into too much detail here, but you incubate at 10 times over the IC50 to point to a tenth of it. You see this is the same curve you saw before, but you also need to do it at a couple other concentrations. You do that to make sure that the residence times that you get out of this are actually consistent across the board, because if things are quite high, you can have rebinding, which will affect your measured measured residence times out of this. So you fit this equation, which has an initial rate, a final rate, and then a rate constant, which describes how quickly it goes from that initial to the final rate. And this is the full equation that you do the fit to. And that rate constant, K observed, that you get out of that is a good approximation of the off rate. And so that is the off rate that we report, and the reciprocal of the off rate is the residence time. And if you throw in a factor of log 2 into that, you actually can get the half-life for folks who are more interested in seeing it that way. So that's how, I'm looking at my notes here. Let me make sure that I'm covering everything. Yes. So for this experiment, we've got an off rate of 25, 45, and 32 minutes. That's about the error you expect in this kind of an experiment, jump dilution experiments. And that's actually fairly close to, or it's within the range of the various off rates that are reported for lapatinib in the literature. All right, so that is reversible inhibitors. For irreversible inhibitors, things get even more tricky, okay? IC50s are useless for irreversible inhibitors. You really need to report these kinetic parameters. And folks in the protease field know this totally, because there's tons of irreversible covalent inhibitors in proteases. But this has been slow to penetrate other therapeutic areas, especially anti-cancer agents. And you'll often see IC50s in the literature reported for these kinds of compounds, for these kinds of compounds. And if you see that, you know that these folks aren't quite sure of the experiments that they're doing here. So the best measure of potency for a irreversible inhibitor says I'm live. Am I there? There we go. The best potency measure is the inactivation efficiency, which is the ratio of K inact to Ki, and that's K big I, not K little I. Those are two different things. The K big I is actually the concentration that you need for half maximal covalent bond formation. That's not half maximal binding, half maximal, which is the K little I. It's actually half maximal of the covalent bond formation, whereas the K inact is the maximal rate of inactivation by that inhibitor. Okay, and so what we do with this is we do a 24-point, 1.5-fold dilution series, and we plot all of those progress curves at once, and we do a global fit to this, and that gives us a whole wealth of information. And it's important to note, and we cover this in other places, if anybody's interested in more information, you need to know whether you can extract a one-step fit versus a two-step fit out of this. If it's a one-step fit, then basically you can only see a linear relationship between the inhibitor concentration and the rate constant that you measure out of this, and that means you can only get K inact and Ki, K inact over Ki. However, if you actually can get a two-step fit, then you can get K inact and Ki separately, which is even more helpful for medicinal chemists that are driving their synthesis by structure kinetic relationships here. We do that by doing a statistical analysis of fits to either of these two models. The one that looks like the best, that's the one we report. So in this case, for lazertinib, we have a two-step fit. We can report K inact and Ki separately, and of course also report the ratio for those two. So that's what I've shown you for the various EGFR inhibitors. I just want to cover a few extra points before I pass it off back to Michelle. Really, the continuous assays that we use here, they offer more accuracy and precision. It's not an endpoint assay where that final read is an estimation, is a cross your fingers hope that it is proportional to the actual reaction rate, which is what you need for enzymatic, for enzymology here. But as we've seen, there's an awful lot of curvature in these progress curves. So if you're working from an endpoint assay, you can actually lose a lot of information there. However, because we're actually getting an actual rate as opposed to a single reading, maybe in duplicate or triplicate at one point, you can have a lot more confidence in that measure, which leads to higher accuracy and precision of the data. So this allows us to have more confidence in both our potency and selectivity. And the TDI workflow that we described, that quickly identifies this novel mode of action, and then you can actually exploit that mode of action. There's a lot of interest in this lately, in this mode of inhibition that we do here. And then it allows you to report the kinetic potency parameters, which for irreversible inhibitors are residence time or half-life, and for irreversibles is the inactivation efficiency. If you're using IC50s, you may not be capturing the true potency, and your SAR could lead off in a different direction. And so even with our kinome profiling, single concentrations, you can actually get a quick peek if there is any time-dependent inhibition, which will suggest that you can actually use this kinetic format to further characterize your hit compounds, and that leads to really interesting ways of moving forward in all of this. So look, this is like I said, this novel mode of action can lead in good new directions. You get advantages not only in potency, but in selectivity and also in PK/PD. All of your measures, once you hit your animal studies, you are actually area under, and you're no longer driven by area under the curve measures. It's Cmax driven, so that allows you to actually wash away the compound naturally in the bloodstream while maintaining target coverage for an extended period of time. And if you're trying to optimize a compound for this, you need to recognize that if you're using an endpoint assay, and we enzymologists have known this for some time, and we've been preaching this for a while, but the number of tools available to us hasn't been too big of a toolbox or too reliable of a toolbox. With our continuous assay format, you can see things that are totally invisible with the endpoint assay. Okay, so that's me stepping off my stump there for that, but I'm going to pass it back to Michelle.
So Earl, I'm telling you, I could just listen to Earl forever and ever and ever. So thank you so much. So we just wanted to point out one more time that today we clearly focused on potency profiling and TDI. We have lots of other applications, so if there's any interest in other applications, you can go to the next slide, Earl. What you have here is you have contact. You can go to our website. Thank you, Earl. You can go to the website where we have separate pages that outline kinome profiling, TDI, our other applications. We have a very powerful resource page that will have other webinars that we've done, some videos, posters, publications. Earl and our door or phone or email is always open, so please feel free to reach out to us. Also, we have a dedicated email address for questions, comments, requests, anything that you want to talk to us about, and that address is hello@assayquant.com. And so with that, I'm going to go ahead and turn it over to Kelsey for Q&A.
All right, thank you, Michelle and Earl. All right, let me start to go through some of these. So we have a couple questions that are a little bit related, and I encourage everyone to keep sending them in. One of them, great webinar, I learned a lot. So kind of two parts here, I'm combining two of the questions. One, can you give this presentation to my team separately? And then two, is it being recorded? And if yes, is it available? So I think, Michelle, you can probably answer that one.
Sure. So with regards to can we give this presentation to your group? Yes, we would love to. We would love to engage in conversation. We can give this presentation, but better yet, we will tailor our presentation to whatever applications that you're working on, what your goals are, and then have a free discussion at the end. So absolutely, we would love to present this to you and love to meet you. With regards to is this being recorded, the answer is yes, it is being recorded, and it will be made available to everyone who is in attendance.
Yep. Yeah, we'll be sending out the email to the link, and then it will also live on our webpage if you ever want to look at it again. All right, this question is probably for Earl. For your kinome profiling work, you use some seemingly unique concentrations of each EGFR inhibitor. Can you talk more about one, what inhibitor concentrations you would typically use for an NCE, and two, if you recommend performing the experiment at at 2 different ATP concentrations, as we showed?
You're on mute.
We definitely will do a dose response test in our assay format with our enzyme construct, with our peptide substrates, before we recommend a concentration for kinome profiling. You can go right in blind and just cross your fingers, but we tend to generate an IC50 first and then do our kinome profiling at a concentration about 10 times over that IC50. And so that's what we recommend to folks. In terms of what experiments to do in parallel, you can get a quick read. You get more information if you do it at both ATP concentrations at 1 millimolar, close to physiological, or if you do it at the KM for each individual enzyme. That will give you a quick take on the mode of inhibition of that enzyme, how ATP competitive it is. And then also we do recommend a couple of different concentrations in case we miss with the IC50 concentration, go a little bit higher and a little bit lower than 10-fold over our measured IC50. If you go for those 4 parameters, that gives you a really good first peek at the selectivity of your NCE.
Thank you.
Did I cover everything there? Yeah.
I think so. And while we have you, for all the nonlinear kinetic curves, how do you fit the rate non-first order to calculate the IC50?
Just the IC. Oh, we actually have a really sweet automated linear range finding algorithm that we use. You got to realize there are so many progress curves because all of those are done in duplicate for kinome profiling for 400 enzymes and seven compounds per plate. You do the math. If you had to eyeball and pull out your ruler old school and find the rate like people did in their biochemistry classes or whatever, you go blind. So what we have an automated linear range finding algorithm, and there's more information about this online if anybody's interested in learning it, that basically walks up and down the progress curve, finds the maximal rate, and then goes in one direction and the other to find out when it starts deviating from linearity based on a certain confidence measure. And once we define the top and bottom of that range, we say that's the linear range from which we're extracting the slope. And so that's how we get the slopes in an automated fashion from all of our progress curves.
Thank you. We have another question about other types of enzymes. So do we have assays for phosphatases and lipid kinases as well?
Yeah, we kind of focused on protein kinases here, but I'm sorry, you want to cover this? Go for it, Michelle.
No worries. You can jump in at any time. So the answer is yes, we do have assays for phosphatases. I believe our list is up to 33 at this time. We also
34.
have, what is it, Earl?
34 as of yesterday.
Oh my goodness, I'm so far behind. So 34 phosphatases, also lipid kinases. We have a great assay for DGKs. How many DGKs, Earl?
There are 10 isotypes, and our confidence in them varies from really good to we'll give you the data, but we're not 100% sure. Those are good assays, and we're getting there. We're also looking hard at phosphatidylinositol kinases. PI3K is a common one that people are asking about. We're hoping we can find something there. It's a little bit tough, as you might imagine, because when you start with a phosphorylated substrate, you're going to get a high background. So we're crossing our fingers, and that's part of one of our R&D exercises to see if we can get a PhosphoSens assay for the PIs.
Awesome. All right, let me For the kinome profiling data that we've shown, the ATP should not wash off the irreversible inhibitor, off if given a long enough pre-incubation time. Is this correct? What pre-incubation time do you use?
That is 100% correct. What you were seeing there is most likely either there wasn't a long enough pre-incubation time for the concentration that it's used, because the rate of inactivation is dependent on both the inhibitor concentration and the time of the inhibition, right, as well as the repetitive nature of the ATP concentration used. So either it wasn't incubated long enough, and so that rate wasn't captured, or, and which is definitely the case here, at the lower compound concentrations, okay, you've already hit all of the enzyme that's as you've already used as much of the enzyme as you can at those concentrations, and there's leftover as much of the compound as you can, and there's leftover not inactivated kinase that can still have a residual rate. So it isn't that it wasn't incubated long enough. It's that you don't have enough compound to inactivate all of the kinase that's in there, and the rate that you see is just the wild type uninhibited kinase doing its thing because it hasn't been inactivated. I wish this was real time, because I want to make sure that the questioner was satisfied with that.
Well, if not, feel free to put it back in the chat and we can discuss more. Another one, I think, Michelle, you started to touch on this in your section, but do we only run these assays, or can they run them in-house? Can you kind of just describe a bit about how that works?
Sure. So every application, including what we presented today, can be run in your lab, except for kinome profiling. And that is because you can imagine that we have 402 kinases in our panel. So that means that in massive parallel fashion, we're running 402 optimized assays. So all the research that goes into that, all of the management of the enzymes and the compounds and all the reagents and the automation that goes into that. So profiling is in our hands. Everything else can be in our hands or yours. And so the actual catalog product is that PhosphoSens sensor peptide for your kinase or phosphatase. So that's the actual assay, or product, if you will. It's the sensor peptide itself.
All right. Thank you. I think that covers all of our questions that we have in the Q&A. We can stay around for a few minutes if anyone has other questions, or they want more information. They weren't satisfied with Earl's answer on that one. But if not, thanks for attending. And as Michelle pointed out, feel free to reach out to us, visit our website, or contact us if you have any other questions or want to learn more. All right, since it looks like there's no more questions coming in, we will end it. Thanks everyone for attending.
Thank you very much,
Thanks a lot,
everyone.
Kelsey. Thank you, Nicole. Thanks both.